hydroxide. All right. So let's say in a flask we have 3 grams of sodium hydroxide pellets dissolved in water. All right, so we do the titration with phosphoric acid. And it takes 62 milliliters. And the question we want is, what is the concentration of the phosphoric acid? All right, so these are the steps that we're going to go through. Step 1 is going to be writing a balanced equation. Step 2 is going to be calculate moles of sodium hydroxide. And then step 3 is going to be calculate moles of phosphoric acid. And then step 4 is use the molarity formula to find the molarity. All right, so this is the last step. And the molarity formula is molarity equals moles of solute divided by liters of solution. So the first 3 steps are just to get moles of solute. The last step, liters of solution, that's given our problem. It is given right here. And then the other thing that's given is 3 grams of sodium hydroxide are in the flask. Oh. So if I was to kind of draw the setup, it would look like this with the burette. So that's got a liquid in it. And then we've got our flask. And then we've got dissolved sodium hydroxide in there. Come on. So we've got sodium hydroxide in there, and in there is the phosphoric acid. So that's how we've got it set up. So we know how many moles of sodium hydroxide because, or we can calculate that because we know how many grams we have. It's going to be 3 grams. Doesn't matter how much water we have in there because we just want to know when we've done a mole-to-mole match. Mm-hmm. And then with phosphoric acid, we know the volume. And of course, we can't use milliliters. We're going to have to use liters. Mm-hmm. All right. Any questions about this part?
No questions.
Okay. So we'll go ahead and get started on this. So the first thing we're going to do is we're going to write the balance equation. All right. So we've got sodium hydroxide. Well, we've got phosphoric acid.
Mm-hmm.
So to do phosphoric acid, we have to know that it's got phosphate in it. We have to know the charge on phosphate. The charge is 3-. So this is just memorizing those polyatomic ions. And then we have H mixed with PO4. H's are +1, PO4 is 3-. So it's going to take 3 H's to balance out that negative charge. So that'll be H3PO4. And that's aqueous. And we're going to add that to some sodium hydroxide.
For our test, will we have to do something like this, like kind of like the polyatomic ions and?
Yes.
Okay. Okay.
Yes. Very possibly.
Okay.
Let me drag this out a little bit longer.
Professor, I just had a question about like what is the difference between like the AQ and the liquid? Like what's the difference?
That is a good question. All aqueous things are liquid. The difference is that aqueous means it has a salt dissolved in it.
Oh, okay.
So aqueous means it's a mixture, not a new compound, but a mixture with something dissolved in the water. Liquid is going to be a compound or something like that. It's going to be a liquid, either compound or element. Now, obviously, the aqueous solution is liquid, but they put aqueous because it's a particular type of liquid.
Mm-hmm.
And with the water, they put liquid because it's a molecule in the liquid state, if that makes sense.
Okay. Yeah, it's kind of like making sense a little bit because I was confused.
Okay.
Okay.
Yeah,
That
so
helps.
imagine if you took salt from your salt shaker and you put it in some water, you shook it in the water, and you stirred it up. That would be an aqueous solution. And you can tell it's a mixture because if you evaporate off all the water, your salt will be left behind.
Oh, okay.
So you can get it back. But with the water being a liquid, you can't do anything to get the oxygen to go away by just changing physical properties. You have to do something chemical to it. So you have to like hit it with electricity or something like that.
Oh, okay. Thank you.
You're welcome. All right, and so we are going to balance this. Oh, come on. All right, let's see what we've got so far. So we've got hydrogen. We've got phosphate. We've got sodium. And we've got oxygen. Now, the reason I'm not doing hydroxide and instead am taking it apart is because on the left we do have sodium hydroxide, but on the right we don't have hydroxide anymore. Now we have water. technically you could still do hydroxide if instead of H2O you wrote HOH. Then you could kind of imagine that, but it's not quite the same thing. So I'm doing phosphate as one whole chunk because there's phosphate on the left and there's phosphate on the right.
Oh, okay.
So I'm going to count up the hydrogen. On the left, we've got 4. We've got 3 in the acid and 1 in the sodium hydroxide. We've got 1 phosphate. We've got 1 sodium and 1 oxygen. And on the right, we've got 2 hydrogen and 1 phosphate and 3 sodium and 1 oxygen. Now, we really have 5 oxygen, but since I'm considering phosphate its own little thing, I include those oxygen with phosphate.
Okay.
If that makes sense. All right, so now we can start anywhere we want to. Usually I like to balance, if there's a metal, I like to balance the metal first. I always like to balance oxygen last. You can balance it in any order that you want. It's not wrong if you start somewhere else. For example, we can start with trying to balance the hydrogen first. Instead, let me change colors. All right. So to do that, we've got 4 hydrogen on the left. So I need 4 on the right. So to do that, I need to recount everything. So it's going to be 4, 1, 3, and 2. And then I can balance the sodium next. So on the left, I have 1, and on the right, I have 3. Put 3 there. So I'm going to move it down a little bit. All right, so I'm going to count everything over here. So still got 4 hydrogen and 1 phosphate. And, oh, you know what? I don't have 4 hydrogen anymore. I have a different number of them. All right, I will need to count that again. So I've got 3 hydrogen in phosphate and 3 hydrogen in the hydroxide part of the sodium hydroxide. So there's a total of 6 hydrogen on the left now. All right. So we've got 3 sodium over here and 3 oxygen. All right, so now our sodium is balanced, our phosphate is balanced, but hydrogen's not. So we're going to go back and change that. So we're going to change it from a 2. Oh, why am I 3 in the way? Yeah, just need to make this smaller. All right. And so what do you think we should put in front of the water to get 6 hydrogen?
3.
All right. So then we have on this side 6 hydrogen and 1 phosphate and 3 sodium and 3 oxygen. So now the whole thing is balanced. So I could have started at sodium or hydrogen or phosphate. I could even have started at oxygen. And we'll eventually get to the right point. All right. Do you need this for a second, this chart, or do you want?
I got it.
Okay. All right. So we'll do our calculations below this little line here. Doing it brown. Brown's good color. All right. So the first thing we had to do was convert our grams of sodium hydroxide to moles. Now, how do I know that I'm not going to start my calculations with the volume of phosphoric acid?
Is it because like it's the final one since they're asking us for the molarity as a final?
Correct. They're asking us about the molarity. So you can go volume to moles if you have molarity. But we don't have molarity, so we couldn't use the 62. But we can go from grams to moles using the molar mass. So that's easy enough. So we'll start there. All right. So we go grams to moles, moles to moles. That's all I need. So now we just need the molar mass of sodium hydroxide. So sodium is 23, and oxygen is 16, and hydrogen is 1. So that is a total of 40. Scoop this over a bit. Oops, too far. Okay. And that's molar mass is always grams per mole. All right. So now we want to go moles of sodium hydroxide to moles of the thing we're trying to find the molarity of. So we're trying to find the molarity of phosphoric acid. So we don't know that. And we knew that we had 3 grams of sodium hydroxide. Okay. So we're going to move to moles of phosphoric acid. So how many moles of sodium hydroxide? So what should we put, what number next to sodium hydroxide?
Should we put the 3?
Yes, it's perfect.
Okay. Are we doing like the mole ratio, is that correct?
Yes,
okay.
Mole to mole ratio, correct. So we're using the coefficients. Oops, all right. So then we put this in the calculator. So it's 3 times 1 times 1 divided by 120. And I don't know what that is off the top of my head. Do you have a calculator handy?
Yeah, I got 0.025.
Okay. All right. So we know that at the end, there should be enough, approximately enough sodium hydroxides to match with all the phosphoric acids. And just going back to check and make sure that everything canceled properly. Got grams of sodium hydroxide canceling nicely. And then, I forgot to put units here. That was moles of sodium hydroxide. Okay, so that leaves us in moles of phosphoric acid, which is good. All right, so the next part is to put it into our molarity formula. So moles of solute over liters of solution. So our solute for the phosphoric acid is the phosphoric acid itself. So that's going to be 0.025 moles of H3PO4 is our solute. And then liters of solution, we've got that we have 62 milliliters. So how would we convert that to liters?
Would we multiply by the 10 negative 3?
Yes,
okay.
Correct.
I got 0.062. Okay.
Good. Yes. Oh, come on. Okay. And so what do we get for the molarity there?
I got 0.403 and then 225806. But then 225806.
Yeah. So we'll just stick with 0.403.
Okay.
Technically, since we have 3 grams and it doesn't give us any more information, like it doesn't say 3.00 or something, technically we should just be one significant figure.
Oh.
So I guess I really should go down to 0.4.
Okay.
And that's the answer to the question, 0.4 molar. So the first step is balance the equation, or write a balanced equation. The next step is convert to moles, and of the thing you know, of the titrant, and then convert to moles of the analyte, and then divide by liters of the analyte.
The analyte is the I remember we did it in class. It was like the unknown concentration, like kind of?
Yes.
Okay.
So the titrant, we know how many moles we have. We don't necessarily always know what the molarity is, but we do know the number of moles. For example, in this case, if we had taken solid sodium hydroxide and put it in the flask and added water to it, but we weren't adding a specific amount, then it wouldn't really matter how much water, because we know at the very end we're still going to have a 1-to-1 match. So depending on, how many moles of the phosphoric acid took.
Oh, okay. Interesting.
Do you want to see one where both things are, well, we know the molarity instead of the grams?
Yeah, we can try to a different one.
Okay.
The one that you said.
Do you need any of this?
I got it.
Okay. Let's see. All right.
Professor Kelly, I remember in class you were talking about that we can use the MV and then V1 equals M2 V2. Is that like when it's a given?
We can only use it if we have a 1-to-1 ratio with everything.
1-to-1 ratio with everything. Okay,
Yeah.
Okay.
Okay, so let's come up with something new. All right. Let's say we have 18 milliliters of 9 molar HCl is titrated with, we'll do sodium hydroxide.
Mm-hmm. So, it's not like NA.
All right. So here we have 18 milliliters of 9 molar sodium hydrochloric acid is titrated with sodium hydroxide. When the indicator changes colors, and we have phenolphthalein, so it turns pink, I think, when it's acidic. Or does it turn pink when it's basic? I don't know. Anyway, it changes colors. When we put in 34 milliliters of sodium hydroxide. So we're going to figure out the molarity of sodium hydroxide.
Oh.
So we'll pull out the information that we know. We know the volume of sodium hydroxide. We know the volume of hydrochloric acid and the molarity of hydrochloric acid. So we know that our second step is always to go to moles of something. We don't necessarily know moles of what yet, but moles of something. So in the first step, we have something converting to moles. We have two options here. We have hydrochloric acid, and we have sodium hydroxide. So which one of those could we actually get moles out of with the information we're given?
Do we use the HCI?
Yes, we could use the HCl because we have volume and molarity. To get moles, you always have to have volume and molarity.
Okay.
Right. All right. So we're going to start with the 18 milliliters. So it's going to be 0.018 liters of HCl. And the molarity was 9 molar. So in 1 liter of HCl, that means there are 9 moles. Of HCl. Wow, that's not what I wanted it to do. What did it do that for? Okay. And then we need to go from moles of HCl to moles of sodium hydroxide. All right, and how would we do that?
Would we put 1 mole of HCl and then would we put the molar mass of the NaOH?
That's a good guess.
Okay.
Actually, we're going to use the coefficients of the balanced equation.
Oh, yeah.
So we're going to write out the equation. All right, and this one just so happens that it's balanced already. So it's a 1-to-1 ratio. All right. So how many moles of sodium hydroxide did we end up with?
Calculating. 0.162.
All right. All right, and we'll check to make sure everything canceled like it's supposed to. Liters canceled. Moles of HCl canceled. All right, so that's good. So moles of solute, so that would be sodium hydroxide. All right. And how many liters of sodium hydroxide did we have?
0.034.
Yes.
Let me get I got, let me see, 1, 2, 3, 4.764.
Okay, that sounds about right. It should be pretty high.
Yeah, there's more numbers.
Yeah, this is good.
Okay.
All right. So that's how to do those. There's a couple other things they could ask. We've got about 10 more minutes. There are a couple other things they could ask. They could ask things like, how many grams of sodium hydroxide? Instead of asking the milliliters, the molarity, they might say, how many grams of sodium hydroxide are in 34 milliliters of sodium hydroxide if 34 milliliters of sodium hydroxide is used to titrate 18 milliliters of 9 molar hydrochloric acid. So it's basically asking the same thing, except instead of molarity, it wants grams. So we would go to grams using molar mass.
Okay.
So on the next page, I can just give you kind of some pointers on how to do titrations and like the steps. Does anybody need, do either of you guys need this page?
I got everything.
You got everything?
Yes.
All right. Okey-doke. So with titration, the first step is balance the equation. Apparently I've hit my caps lock. I'll just keep it. All right, and the second is to find moles of the titrant. And a titrant is the one we know how many moles we have, or how many grams, or the molarity, or something like that. So titrant, we can calculate how many moles we have.
Okay.
Okay. And then the third step is to go from the moles of titrant to the moles of analyte. So you're going to find the moles of analyte from the moles of the titrant using the coefficients of the balanced equation. And the analyte is what you're looking at, is what you're looking for.
What happened?
So you don't know how many moles of that.
Okay.
Or maybe you know how many moles, but you don't know how many liters. You know, that kind of thing. And then
Okay.
the last step, if you're doing a traditional titration, is just to divide the moles of the analyte over the liters of the analyte. And then that will give you molarity.
Oh.
All right. The long method always works also. So if you want to always use a long method, you can do that. I tend to always use a long method just because it's like a habit at this point.
Yeah.
So what last minute questions do you guys have?
Is that 1-to-1 ratio like in that balance equation? It's like it's just 1 there. Is that correct? Okay. And that coefficient. Okay.
All right. Yeah, for coefficients.
Okay.
That is a good question. There you go.
Okay.
Got like 4 more minutes.
I think that's all I have right now.
All you have? All right.
Hi, Professor.
Yes.
Can I ask you some question about the like this